we are getting online in 3, 2, 1. Ok, ótimo. Bem, boa tarde a todos os presentes e a todos que estão nos assistindo online via YouTube. Meu nome é Rodrigo Nemmen, eu sou professor no Departamento de Astronomia do Instituto de Astronomia, Geofísica e Ciências Atmosféricas da Universidade de São Paulo. Vamos dar início à defesa de doutorado do candidato Raniere Maciel de Menezes. O título da tese de doutorado é Explorando o Universo Extremo com o Telescópio Espacial Fermi, da qual eu fui orientador. Essa defesa de doutorado ela será inteiramente online, seguindo as recomendações, é claro, da Organização Mundial de Saúde, do governo do Estado de São Paulo, a fim de evitar aglomerações e assim maximizar a segurança de todos nós em relação à pandemia de Covid-19. O candidato terá o máximo de 1 hora para fazer a sua apresentação da sua tese de doutorado, que será seguida pela arguição dos membros da comissão julgadora. E os membros da banca julgadora são os seguintes: o professor Fabrizio Tavecchio, do Instituto Nazionale di Astrofisica em Brera, o professor Francesco Massaro, da Università degli Studi de Torino, a professora Ana Leonor Quis Santiago Santos, da Universidade Federal do Rio Grande do Sul, a professora Zulema Abraham, do IAG da Universidade de São Paulo, e o professor Gastão Cesar Bierrenbach Lima Neto, também do IAG.USP. E eu gostaria de pedir a todos os presentes que desliguem seus microfones durante a apresentação do candidato. E agora eu vou fazer, como essa vai ser uma defesa em inglês, e nós temos membros não brasileiros, eu vou agora fazer a apresentação em inglês. Let's begin the PhD thesis defense of the candidate Raniere de Menezes in the Astronomy Department of Instituto de Astronomia, Geofísica e Ciências Atmosféricas of University of São Paulo, entitled Exploring the Extreme Universe with the Fermi Large Area Telescope, which was done under my supervision. This PhD defense will be entirely online, following the social distancing recommendations of the World Health Organization and the São Paulo state government, in order, of course, to ensure the safety of us all with respect to COVID-19. The candidate will have 1 hour for the oral defense, for the oral presentation, and the presentation will be followed by questions from the thesis committee, which I already listed. I would like to ask everybody to please turn off their microphones during the oral defense. And now I give the online floor to the candidate. And Raniere, you may begin sharing your screen and begin with your presentation, please. Thank you.
Thank you, Rodrigo. Can you see my presentation?
Yes, something is happening.
Yes.
Yeah.
Okay. Thank you, Rodrigo, and hello, everyone. Good afternoon. I am really glad to be here, and I hope you can enjoy and maybe learn a little bit with the results of my thesis. Over my PhD, I used gamma ray observations made with Fermi Lat to explore the high energy emission from globular clusters, low luminosity active galactic nuclei, unassociated gamma ray and unassociated gamma ray sources. Hence, I'm dividing this presentation into 5 parts. I will start by giving you an introduction about the gamma ray sky in the Fermi era. Then I'll talk about globular clusters, low luminosity AGNs, and finally, unassociated gamma ray sources. In the end, I will summarize everything, show you my plans for the future. Since its launch in 2008, Fermi Lat has detected blazars, pulsars, supernova remnants, high-mass binary systems, globular clusters, radio galaxies, star-forming galaxies, pulsar wind nebula, and a lot of other types of sources. And these gamma ray observations are fundamental to assess phenomena such as the jet launching by AGNs, the acceleration of particles in the magnetospheres of pulsars and even black holes, and the interaction of cosmic rays with the interstellar medium, resulting in gamma ray emission from pion decay. The very first problem of gamma ray astronomy arises with the opacity of Earth's atmosphere. The gamma rays simply cannot make their way to the ground. As you can see here in this figure, the opacity of the atmosphere is 100% in the gamma ray band. So direct observations of gamma rays can only be made from space. However, we have ground-based observatories which can detect gamma rays in an indirect way by observing the blue radiation from particle air showers. Once a gamma ray enters in the atmosphere, it produces a shower of relativistic particles. And these particles travel faster than light in this medium, in the atmosphere, therefore emitting what we call Cherenkov radiation. This flash of radiation lasts for only a few nanoseconds, and our telescopes on ground can then detect the shape of this cascade from the Cherenkov light and reconstruct the energy and direction of the incoming photon. The working medium of these telescopes are the atmosphere, and in some cases, water tanks. For the atmosphere, the best examples today are MAGIC, Veritas, and HESS, and CTA in the near future. And for water tanks, the best example we have is HAWK in Mexico. In the case of Fermi Large Area Telescope, or Fermi-LAT, direct observations of gamma rays are made from space. And the telescope is divided in three main parts. The tracker, represented here by this tower. There are actually 16 towers. It's an array of towers. The calorimeter, which goes in the bottom of the telescope, and the anti-coincidence detector or anti-coincidence shield, which covers the whole telescope. Once an incoming gamma ray enters in the tracker, it produces in one of the 16 tungsten layers that are in the tracker. You can see the layers here represented in this figure. So the photon produces, and the electron positron from this gamma ray will leave an ionized path in adjacent silicon strip detectors. And we can map this ionized path to reconstruct the direction of the incoming photon. And once the electron positron reach the bottom of the telescope, where there is the calorimeter, the optical depth is very high. So a cascade similar to what happens in the atmosphere is developed in the calorimeter. And the calorimeter then can measure the total energy of the cascade and reconstruct the energy of the incoming photon. At last, we have the anti-coincidence shield or detector, which is the first line of defense of Fermi-LAT against cosmic rays. Once a cosmic ray, a charged particle, crosses the plastic tiles of the anti-coincidence detector, the cosmic ray releases a very short flash of light, which is detected by the telescope, and then the telescope knows that the particle going down the tracker is a cosmic ray and not a photon. So we can filter the cosmic rays due to the anti-coincidence detector. The effective area of Fermi-LAT increases with the energy of the incoming photons. And the better trade-off for the telescope is around 1 giga-electron volts, where the effective area, as you can see here, is around 1 square meter, and the number of counts is still very high. So the gamma ray sources still emit a lot of photons. The telescope works in the energy range from 20 mega-electron volts up to more than 500 giga-electron volts, and its field of view encompasses 20% of the sky on a single shot. Fermi to make an all-sky survey every 3 years. The resolution of Fermi-Lat, it depends on the energy of the photon and on the amount of counts we have from a certain source. So this resolution can vary actually by 2 orders of, and it can be as good as a few arc minutes and as high as 1 degree. Here you have the resolution for the detection of a single photon at 1 giga-electron-volt. After 10 years of observations, Fermi-Lat has detected more than 5,000 sources, and most of these sources are blazars. Indeed, around 60% of the last catalog of Fermi-Lat is made up of blazars. The rest of the sources are non-blazar AGNs, pulsar supernova remnants, pulsar wind nebula, globular clusters, and many others. And interestingly, 25% of the catalog is made of unassociated gamma-ray sources, which means that they lack a counterpart in other wavelengths. We have the point-light gamma-ray source, but we don't know which source in lower energies is responsible for this gamma-ray emission. In this figure here, you can see the Fermi-Lat all-sky survey, and the blazars, they are scattered over the whole sky, while the pulsar supernova remnants and pulsar wind nebula, they are all distributed in the galactic plane as they are galactic sources. This high emission you are seeing here from the galaxy is coming from the interaction of cosmic rays with the interstellar medium, which means these are gamma rays from neutron pion decay, mainly. Among the sources detected by Fermi-Lat, there are globular clusters, which are evolved collections of stars, of thousands to millions of stars, tightly bounded by gravity. And the stellar density, the number density of stars in the cores of globular clusters is so high that dynamical interactions between these stars is something really common. And this is important for the gamma ray emission of the cluster, as I will explain soon. The very first cluster detected in gamma rays was 47 Tucanae, and it was detected by Fermi-Lat. But since then, we have 30 detections of globular clusters, as listed in the second data release of 4FGL. The underlying mechanism behind the gamma ray emission from globular clusters is the high number of millisecond pulsars they contain. And these millisecond pulsars are formed by stellar flybys. When these flybys produce close compact binaries in a mass transferring regime, like shown here in this artistic depiction, where we have a neutron star swallowing matter from a main sequence donor and speeding up, and if it speeds up enough, it can reach periods of millisecond pulsar and then of milliseconds and then light up as a pulsar. And the gamma ray emission from the millisecond pulsars is likely coming from the magnetospheric gap via a process that we call curvature radiation. In orange here, you can see the outer magnetospheric gap in the surroundings of a millisecond pulsar. And the outer gap is formed in the edge of the light cylinder, where the magnetic field lines cannot close anymore. And the electric potential drop along the gap is so high, is of the order of 10 to 17 volts, that they can easily accelerate electron positrons up to the relativistic domain. And these particles then can emit the curvature radiation, which is similar to synchrotron, but it's not the same. And in this figure here, you can see the gamma ray spectrum of a globular cluster, Terazon 5. And this spectrum is exactly what we expect from the sum of many spectra of individual millisecond pulsars, just supporting even more this hypothesis of the millisecond pulsars behind the gamma ray emission of globular clusters. But there is a problem with the stability of binary systems in the cores of globular clusters. Once a binary is formed, it may undergo subsequent encounters depending on the dynamical parameters of the cluster. And these subsequent encounters can disrupt the binary systems. Indeed, here we have what we call the encounter rate. You can call it also the binary formation rate. And it's given by this relation here, where n is the stellar density as a function of radius, and sigma is the velocity dispersion of the stars as a function of radius too. And we can simplify the encounter rate by this relation here. And on the other hand, we also have the disruption rate, which is given by this relation and was never tested before. So we are testing for the first time in high energies this correlation here. And the binary lifetime, we expect that it depends on the disruption rate. So the larger the disruption rate, the shorter is the lifetime of a binary system. And if it's short enough, the neutron stars will not have time to evolve into millisecond pulsars. So this is the main question we want to answer in this project. How do stellar encounters affect the gamma ray emission from globular clusters? So to answer this question, we used 9 years of Fermi Lat observations in the energy range from 100 mega electron volts up to 100 giga electron volts. And we tried to observe 150 globular clusters as listed in this catalog. And among these 150 sources, we detected 23 of them. 2 of them never detected before, which are Messier 14 and 79, never detected before gamma rays. And as a quick result, we found that all of the 23 detections have steady light curves, which is expected for globular clusters, because do not expect that a population of millisecond pulsar will have flares or some high variability. So our data really shows that the gamma ray luminosity, you see here in the y-axis, is correlated with the stellar encounter rate, which means that a higher number of stellar encounters indeed increases the gamma ray luminosity and likely increases the formation of millisecond these clusters. From this plot, you may see that we have 4 outliers here, and here, which are NGC 6397, 6752, 1005, and NGC 6316. This cluster here is the only one that we cannot explain why it's an outlier. 1005 we know because we are using the parameters in the Harris catalog to estimate the stellar encounter rate for the source. So it actually should be here, because the parameters as listed in the Harris catalog are quite outdated. They are not very good for 1005 specifically. And for these 2 sources here, we can explain with the next plot. So we found that clusters with a high disruption rate here in the x-axis are faint gamma ray emissions. And if you notice here, the 2 clusters with the highest value for the stellar encounter rate, actually for the disruption rate, are exactly the outliers from the previous plot. So we interpreted this as these binary systems likely being, the binary systems in these clusters likely being disrupted before the formation of millisecond pulsars, and then supporting the scenario of this parameter here, the disruption parameter. The high disruption rate also explains the low number of detections by Fermi Lat. In this plot here, in red, you see the globular clusters detected by Fermi Lat. And you see that all of them are concentrated towards higher values of the stellar encounter rate. But we have a lot of clusters in this region that are not detected by Fermi Lat. And some of them should be. And what we found is that a significant fraction of these clusters, painted here in dark blue, have a very high disruption rate. And by very high, I mean above 350, which in the previous plot means that they are from here to the right. So these clusters are likely not detected by Fermi simply because their binary systems are disrupted before the millisecond pulsars have the chance to light up. And some of the other clusters are simply not detected because they are too far away. So as the summary of this project, we found that the gamma ray emission can be estimated in terms of the dynamical parameters of the cluster. We found that the disruption rate seems to negatively affect the gamma ray emission. And as a minor result, we found we detected 2 new globular clusters. The details of this analysis can be found in this paper that we published in the monthly notices of the Royal Astronomical Society in the last year. Now I will start the second project of this thesis, which is about low luminosity AGNs. And the very first thing I want to make clear for you is that low luminosity AGNs are not scaled down versions of quasars. Let me call quasars and Cephers as classic AGNs, as you can see here in this figure. And the accretion disk for these sources is optically thick and geometrically thin. And these disks are also relatively cold. Their temperature ranges from around 10,000 Kelvin up to 10 million Kelvin, depending on the mass of the black hole. The higher the mass of the black hole, the lower the temperature of the disk. And the spectrum that we observe from this thermal emission is a spectrum of integrated black body radiation, which in the case of supermassive black holes gives a peak in the ultraviolet that we call big blue bump. The luminosity of these classic AGNs is directly proportional to the accretion rate, and this kind of scenario is possible only when is physically possible only when the accretion rate is less than the Eddington accretion rate and larger than a few percent of the Eddington accretion rate. But in the case of low luminosity AGNs, we are in a very different system, in a very different scenario. We are in the radiatively inefficient accretion flow mode, or RIAF mode. And the RIAF is optically thin and geometrically thick. It's exactly the opposite of the classic AGN case, what we call a Shakura-Sunyaev disk. And the density of the gas is so low that the gas is very inefficient in cooling and presents a two-temperature plasma where the ions have a higher temperature than the electrons. In this case, we call this system a hot accretion flow because the temperatures are really, really high if compared to the previous case. So in this case, the temperatures, they are basically the virial temperatures. A typical black hole mass, a temperature of 1 trillion Kelvin for the ions. In the case of the luminosity of a RIAF is proportional to the square of the accretion rate, and not simply to the accretion rate as in the previous case. One interesting thing to notice SEDs of low luminosity AGN is that they lack a big blue bump. Here in orange, you see the average SED for a population of low luminosity AGNs. And they don't have a big blue bump because they don't have the Shakura-Sunyaev disk. So the emission is not from the integrated black body radiation. And another interesting thing about these SEDs is that on average, the low luminosity AGN are radio loud, as you can see here, if compared to quasars and Cephers are shown here in these other curves. And a last thing that is interesting to notice about low luminosity AGN is that they are very efficient in launching radio jets. So what about the gamma rays? The gamma ray emission is predicted to be originated in the INAF via a process that we call pion decay. And this is predicted because RIAFs are so hot that proton-proton interactions may be very common, and these proton-proton interactions can form neutral pions, which quickly decay in a pair of gamma rays. And these gamma rays are supposed to be detected by Fermi Large. As you can see here in this figure, the gamma ray emission predicted from a system, from a RIAF system, is peaked around 1 gigaelectron-volt, and it fits perfectly in the Fermi Large energy band. This peak is at 1 gigaelectron-volt, but it don't need to be here always, because this peak depends on the proton distribution of the supermassive black hole and surrounding systems. And this is the main question that we want to answer in this paper. Is pion decay really an efficient channel for gamma ray production in low luminosity AGNs? So to answer that, we analyzed 200 low luminosity AGNs from the Palomar survey. The Palomar survey is a nuclear spectroscopic survey, and by nuclear I mean the nuclear region of the galaxies, only in the northern hemisphere and very close to the Milky Way. So in practice, they all have a redshift around 0. And we used Fermi Large observations from August 2008 up to November 2018 in the energy range from 100 mega electron volts up to 300 giga electron volts. And we also used archival radio to X-ray data to better analyze the nature of the gamma ray emission we were observing. So among the 200 sources we tried to observe, only 4 of them, as listed in this table, were detected in gamma rays with a significance above 5 sigma. We have 2 extra detections, but these detections are in a lower significance, so we are not taking them directly into account in our results. The very first result we have is that the gamma ray emission is correlated with the radio emission. And we see that only the brightest radio sources in our sample are detected in gamma rays. And this gives us a hint that this gamma ray emission that we are observing may actually be originated in the jet and not in the RIAF. This is the very first hint. And this correlation here also disfavor gamma ray emission from a magnetospheric gap, because in magnetospheric gap models, the gamma ray emission should be anti-correlated with the radio emission. We also found that strong gamma ray emission does not imply in a high gamma ray luminosity. We can even see a trend here in the detected sources here in red. So you may try to fit a curve here, but it's not a relation that holds for the entire sample. So we know that the jets are emitting a lot of X-rays in these sources here, because you can observe these jets with Chandra. We can resolve these objects in these AGNs with Chandra telescope. But for the rest of them, we interpret these results as saying that the X-rays are coming mainly from the accretion flow itself, which means from the RIAF and not from the jet. So to test the origin of the gamma rays in these sources, we tested 2 different spectral models. Here on the left, we have a synchrotron self-Compton, a synchrotron plus synchrotron self-Compton model fitted to the SED of one of our targets. And on the right, we have the same target, but modeling it as a RIAF. So we see that the synchrotron plus synchrotron self-Compton fits the data way better than the RIAF. It's not perfect, but it fits better. In the case of RIAF, you can see here this green line. In the case of the green line, it's not a fit, it's a prediction. So we see that the predicted gamma ray emission from the RIAF is way lower than the observed data. So based on this, And on this is for the same kind of analysis for another galaxy. So based on this modeling of the SEDs, we find that the gamma ray emission from these sources is mainly coming from the jet. Even if these sources are misaligned with relation to the line. And as a summary of we found that AGNs are detected in gamma rays. Our data disfavors gamma ray emission because we should observe an anti-correlation instead of a positive correlation. Our SEDs are better described by the synchrotron self-compton model instead of the RIAF. And the gamma rays that we observe are likely from a jet origin. This is what we conclude, even if these AGNs are misaligned with respect to the line of sight. You can find the details of this project in this paper that we published in January this year. And finally, I'm going to the last part of this of my thesis, which is related to unassociated gamma ray sources. So this is a very old challenge in gamma ray astronomy, and this problem arises because the typical positional uncertainty of gamma ray telescopes is very high if we compare to other detectors in other wavelengths. In the case of Fermi-Lat, it's typically of 4 arc minutes, but it can reach 1 degree for some sources. And you can see here in these figures that we have a point-like gamma ray source represented by this white ellipse here and here, and we open with ultraviolet and infrared images, and you can see that we have tens of sources that can be responsible for the gamma ray emission that we are observing. So it's very hard to pinpoint the source responsible for the gamma rays we are seeing. Of course, that this problem can be attenuated by the non-thermal nature of gamma ray sources. So for instance, in this case here, if we know that some of these sources here are stars, then we can discard them immediately as the counterparts of the gamma ray source, because stars as thermal sources are not predicted to emit gamma rays in a significant way. So in the case of blazars, which made up most of the sources in Fermi-Lat, we have very specific infrared colors. This is a infrared color diagram, and we can see that the blazars here in red and blue, they occupy a very restricted area of this diagram. So, and this happens because they have a non-thermal emission. So, based on principles like this, we can attenuate the problem that I just mentioned. And once we associate a blazar to a Fermi-Lat source, we can only determine the nature of this blazar if we have the spectra. And sadly, 44% of the latest release of Fermi-Lat catalogs, 44% of the blazars listed there are what we call BCUs, which stands for blazar candidate of uncertain type, which means that they have no spectrum available. This means that we have the photometric points that build up, forming an SED typical of blazars, but we don't know if these blazars are BLACs or flat spectrum radio quasars. And the association method that we commonly find in literature, these methods depend on only on non-physical parameters. And in the case of Fermi-Lat, they typically use the angular separation and integrated flux. As you can see here from this equation, the likelihood ratio computed in the Fermi-Lat catalogs depends only on the angular separation, going here in the exponential, the surface density of objects brighter than the candidate counterpart for the gamma ray source, and on the solid angle encompassed by the lat error ellipse. So there are no physical parameters involved in this equation, and this is something we want to modify. So we focus on the association of blazars by 3 different approaches. First, we evaluate VBRAWS and KDE BLACs as catalog of candidate gamma ray blazars. I will give you more details about this catalog soon. And then we take spectral properties into account when associating counterparts, which means that we are modifying this equation here to account for physical parameters. And in the end, we do spectroscopic observations of BCUs. And this project is a very straightforward project. So VBRAWS stands for Wise Blazar-like Radio-Loud Sources. And this is a catalog of infrared sources selected based on the infrared colors of known gamma ray blazars. And these sources are detected in all 4 Wise filters, and they are required to be radio loud. This gives us a total of about 10,000 sources. And on the other hand, we have this other catalog, the KDE BLACs, which stands for Kernel Density Estimation, Selected Candidate BLACs. And the sources here are also selected based on infrared colors, and these infrared colors are consistent with 93 confirmed gamma ray BLACs. These sources are detected only in the first 3 energy bands of WISE. They are also required to be radio loud, and we have around 5,000 BLACs. So we selected the candidate with spectra available in the archival data of Sloan Digital. And we found that we analyzed one by one more than 1,000 spectra. And we found that VBRAWS is indeed homogeneous, with a minimum of 30% and maximum of 95%, actually 90% of this catalog is composed of blazars. I say that at maximum 90% because we have a lot of TSO objects that we cannot guarantee that they are blazars unless we have information about the radio spectrum, which we do not have. And in the case of KDE BLACs, this catalog is significantly contaminated by normal galaxies. So we see a very high efficiency in spotting blazars for VBRAWS, but for KDE BLACs, the case is not that good. So we have 40% of this catalog contaminated by normal galaxies, and only 20% of it is made of confirmed BLACs. But if we are accounting for the blazars and not only BLACs, this efficiency can range from 30 to 50%. We also found that the BLACs are concentrated in the bottom of the color diagram. So if we need a higher purity catalog, we simply cut this part of the catalog and we increase the purity by around 25%. Of course, losing some completeness. Another result of this work was that we revealed the nature of 11 BCUs listed in 4FGL, and these BCUs are now published in the latest release of 4FGL. And we found this spectra by analyzing the redshift, the spectra in Sloan Digital Sky Survey, and we even were able to give a redshift for most of them. Besides that, we also found 25 new BLAC objects, which will likely be included in the next release of the Roma BZCAT. As a summary of this work, we found that VBRAWS is at least 30% and at maximum 90% made up of blazars. A KDE BLAC is not that good, but it can be at maximum 50% made of blazars. We identified 11 BCUs, which are now in 4FGL, and we found 25 new Bierrenbach objects. You can find the details of this paper, of this analysis in this paper that we published last year in the Astronomy and Astrophysics. Okay, for the second project on this topic, on the topic of associations, we are modifying the association method used by the Fermi Large team. So we start by cross-matching 4FGL with Vibros, and for a given gamma ray source, for an unassociated source, there is only a few reasonable candidates in Vibros. For instance, we have here a gamma ray source with photon index gamma, and for this range of photon index plus minus the error bar, we have only a few Vibros candidates that have the correct infrared colors from these two plots and radio loudness. So the new likelihood ratio computation depends, given by this equation, depends only on the spectral parameters. So the computation of the likelihood now depends on Q, which is the probability to find a Vibro source within these three specified ranges, which are given by this figure here inside these three boxes, and depends on the local surface density also within these specified ranges. So we computed the likelihood ratio formulated in this way for all the cross matches, and then we repeat the process for 500 fake gamma ray catalogs in order to find the correct statistics. So in the end, we computed the association probability for around 1,000 blazars, including more than 200 blazar candidates of uncertain type, and 5 unidentified gamma ray sources. The association probability depends on the distribution of the log likelihood for the fake catalogs, for the 500 fake catalogs, and on the likelihood distribution for the real cross-match, for the 4FGL crossed with Vibros. And this is the result. This is the association probability as a function of the log likelihood. So we have more than 1,000 blazars with a given association probability. The summary of this result is that we developed a new association method, which is based only on spectral parameters. We can associate more than 1,000 blazars with this method. And we give to the community a list with more than 200 BCUs and 5 UGSs, which is ideal for future spectroscopic follow-ups. The caveat with this method is that you can use it only for blazars. So if you want to use it for other kinds of sources, you have to modify it. You can find the details of this project in this paper that we published this year. And for the last project of this thesis, we did up of BCUs as listed in 4FGL and F8Y, which are both some of the latest catalogs of gamma rays. And this project is part of a larger project where more than 350 BCUs have already been observed, giving a huge contribution to the. So we observed 37 BCUs with SOAR and O1 SPM. And all of our targets have infrared colors similar to what's expected for blazars, for gamma ray blazars. As you can see here in black, the black stars and white targets, and they have colors similar to blazar infrared colors. Maybe except for this source here, but I can come to this source later. So we acquired this data, and we reduced this data with IRAF, CCD-PROC, and AstroPy. Most of our targets were found to be BLX. This is one of our targets, and this is the spectrum we took. And it shows that it's a featureless spectrum, which is consistent with a BLAC. You can see here some absorption lines, but these are from Earth's atmosphere and not from the BLAC itself. So the resolution of our observations varied from 400 per millimeter down to 300 lines per millimeter, depending on the case. And as a summary of our results, we detected 25 BLACs among the 37 BCUs we analyzed, and we were able to give the redshift for 10 BLACs, which is something quite hard to do because of the features characteristics of the spectrum. And we found 3 flat spectrum radio quasars, and the rest of them we found to be blazar BZGs, which are BLACs with a lot of contamination from the host galaxies. And we found also 1 normal galaxy, which may be likely a bad association. And this is exactly, the galaxy is exactly the source here, which do not present gamma ray colors, gamma ray infrared colors of gamma ray blazars. And you can find the details of the optical spectroscope campaign in this paper and on the other papers of this series. And that's it. As my conclusions, I have to say that all my projects are related to Fermi Lat. We worked on the formation of millisecond pulsars in globular clusters and on the gamma ray emission, on the predicted gamma ray emission from neutral pion decay in RIAF systems. We tested VBROS and KDE BLACs as catalogs of gamma ray blazar candidates. We developed a new association method, which depends only on physical parameters. And we were part of the spectroscopic campaign where we did direct observations of blazar candidates of a certain type. So for these 3 projects here, I would like to do a stacking gamma ray analysis in the near future. And I'm pretty sure I can extract a lot of physics from these projects by doing this kind of analysis that I'm just learning. And for these 2 other projects, the logical next step is to do more spectroscopic observations, especially because in the case of this paper, we give a list to the community that is very convenient in guiding future optical spectroscopic follow-ups. And that's it. I would like to thank you, and by you, I mean you all who are part of this thesis in a direct or indirect way. I would like to thank you for the opportunities and especially for the friendship. I would also like to thank FAPESP, CNPq, IAG.USP, OAM, UNITO, CFA, and of course the Fermi Lat collaboration. Thank you very much.
So thank you very much, Raniere, for the great presentation. So first I will do the speech in Portuguese and then in English. O candidato terminou sua apresentação oral. Os membros da banca podem agora iniciar a sessão de perguntas. Cada membro da banca, só checando, can everybody hear me loud and clear? Okay.
Yes.
Okay. So, os membros da banca podem agora iniciar a sessão de perguntas. Cada membro da banca terá um máximo de 40 minutos para fazer perguntas. E before I proceed, would you like a 5 minutes break before we proceed, or can we go straight ahead? Anybody would like a 5 minutes break?
I would like.
Okay. So let's do the following. Let's do a 5 minutes break for getting for the candidate to catch his breath. You can get some water, coffee, and we reconvene here in 5 minutes, okay? Thank you.
Okay.
Okay, okay. Thanks.
Rodrigo, what will be the order?
So the order will be first Fabrizio. It's the order of a descending order of physical distance, okay? So first Fabrizio, then Francesco, then Ana, then Zulema, and then Gastão. Okay, so Fabrizio will begin. Okay, Fabrizio?
Okay, thanks.
It's only 1 hour with me and Fabrizio, but
But we are
so
easier
I
than
actually,
this,
I did the calculation, and then Fabrizio is about 120 kilometers farther from us than
yes.
Francesco.
True.
it's less than 1 hour by train, so fine.
It's a very small percentage, but of the total distance. But okay.
Yes.
Okay. Let's reconvene in a few minutes.
Yes, yes.
Oi, Rodrigo. Por que você está 2 vezes? Você entrou 2 vezes?
É que eu estou aqui, estou com 2 computadores aqui.
Os 2 ligados?
Sim, estavam 2 na apresentação. Acho que vou desligar, não desliguei a câmera de um deles.
Aqui tem 2 câmeras.
Tá. Desligar.
Na frente e de lado.
Peraí.
Posso fazer as perguntas em português? Ou...
Opa!
Não. Melhor em inglês, tá?
Olha, se você desejar fazer em português,
Não,
como ele apresentou em inglês.
Não, brincadeira.
Se você sente confortável para falar ciência em português, Fabrício?
Não, nunca falei em ciência, nunca falei. Então.
Vamos esperar. Is everybody back? Anna, are you back? No, Anna, let's wait for Anna.
Yes, I'm back.
Oh, you're back. Okay.
I'm back. I'm
Great.
just now with the camera on.
Okay, so shall we resume?
Okay.
All right. Fantastic. So let me continue. So finish the speech in Portuguese. Cada membro da banca, então, agora terá um máximo de 40 minutos para fazer perguntas. Seguindo a tradição, gostaria de convidar os membros por ordem decrescente de distância física até o IAG, que é a tradição no Instituto, e começando, portanto, com o professor Fabrizio Tavecchio. Agora eu vou do it in English. The candidate has finished his oral presentation. The members of the thesis committee can now begin with the question session. Each committee member will have a maximum of 40 minutes to ask questions, 40 minutes. Following the tradition, I would like to invite members by decreasing order of physical distance from the astronomy department. And according to my estimates, the committee member which is farthest from here is Professor Fabrizio Tavecchio. So I invite Fabrizio to please begin with his questions. Fabrizio, you have the floor.
Okay, thank you. Okay, first of all, congratulations both for the thesis, really well written and clear. Your results that you obtained, and also for the talk today, really impressive. So congratulations. I don't have a lot of questions, but some curiosities, mainly concerning the work that you did on low luminosity AGNs, and particularly the modeling of the non-thermal gamma ray the gamma ray that you expect from RIAFs. So you basically you said that you consider protons in the gas. I don't understand if you consider only thermal protons or there is also a population of non-thermal protons. And if a non-thermal population is considered, how do you normalize this population? Okay. Okay, this is the first question. How does it work now? He replies or?
Maybe
yeah. So after each question, or it doesn't need to be only questions, right? You can make comments.
Sure.
You can talk about anything. We can. It's a very free discussion. And so after each question or comment, the candidate can reply.
Okay, great.
Yeah.
Okay, I'm going to the plot. Okay, in this plot, the protons that we are using to model this gamma ray emission, they are non-thermal. The electrons, on the other hand, are thermal. So this blue line here is a RIAF leptonic model with thermal electrons, which is fitted to the data. And based on this fit, we extract the parameters to predict the gamma ray emission from a hadronic RIAF model. But this is, of course, this is not a fit. This is just a prediction. But in this case, we are using a non-thermal distribution because if we use a thermal distribution, the results will be even lower. The gamma ray emission predicted will be even lower.
Okay, but I think that you have to specify somewhat the parameters of this population. So a slope for the protons, the minimum Lorentz factor, minimum energy, and so on and so forth, and also normalization. Okay, the normalization, of course, is critical here, because if, for instance, normalization is 100 times larger, you basically catch the data. So
yes.
Okay, and so can you explain how do you fix this?
Actually, I don't remember how we did the normalization. I just remember of using the parameters from the fit to estimate the gamma ray emission. Okay, somewhat you are using another code, a code that you get from somebody, I think.
So if I may contribute to the answer, so I was responsible for doing so in this paper, I was responsible for the RIAF for the hadronic emission from the RIAF, and Justin Finke was responsible for doing the self-synchrotron Compton model. Okay.
Yeah.
And in my RIAF hadronic model, I assume that the protons, the power law index in the energy distribution, if I'm not mistaken, is around 2.5 or 2.6. Okay, but it's around 2. I don't remember now the exact value. And to normalize for the normalization, okay, so the proton number density I take I assume that a small fraction of the protons is non-thermal. Okay, so I take the total number of protons as the same as the electron, the predictions of the RIAF model, and then I assume that a small fraction are in a power law distribution, a fraction of a few percent. Now I cannot remember what fraction exactly.
Okay.
But I have all the details, and for computing the pion decay emission, I used the code. I didn't write all the nuclear physics, you know, all the things. So I use a code, which I also forgot the name of the code.
The name is NIMA.
Yes, it's a code, but it's a code. Haronian is a co-author in the code.
Yeah. Okay. Yeah. No, I'm curious just because. The difference is huge. So I think it will be difficult to match the data, but I'm curious if one can turn some some parameter and to go up with this. Okay, thanks.
But I think this will be an interesting project to follow up, to do a more careful evaluation of the RIAF contribution, doing exactly what you are suggesting, Fabrizio. I don't know if Raniere agrees.
Also, yes. Because besides the pi zero, you also produce the charged pion that can produce neutrinos. Yes. And this also is very interesting in view of this ice cube detection. So also because this kind of sources are quite numerous in the nearby universe, maybe that they cannot do the total neutrino flux, but maybe a fraction of it. So the question was, the goal was to understand if one can increase the neutrino output, basically. Okay. Thanks. Okay. Now, another curiosity, at slide 47, when you showed us the spectrum of one of these BLX. I'm not an expert, so probably I'm saying some. At around 2,500 angstrom, you have this. Is not aligned with something.
You say 2005, where?
Where in the 5,500. Yes, this one.
Okay.
This is just noise, cannot be aligned.
No, actually, it may even be aligned, but in this case here, it's useless for us because we cannot compare this line. So
you don't know the line. You say, okay.
Yes. It may be a line. It possibly is a cosmic ray, which was not correctly subtracted from the reduction process, but it can be a line. It's very hard to tell.
Okay, great. Okay. No, for me it's okay. I don't have any other question or curiosity. For me.
Thank you very much. Thank you, Fabrizio.
Thank you.
Thank you, Fabrizio. It's a rarity that a committee member is so direct to the point. Thank you. So now let's
just because I was interested in this stuff. So.
Yes, and also feel free, of course, feel free to interact and ask questions or comments during the rest of the process. Okay. So now let's move to the next committee member. So Francesco, please, you may begin.
Yes. Okay. But I mean, thanks a lot for the presentation. Thanks for the time spent here in Turin. I really enjoyed working with you. I have only very few questions. Okay. So probably and a couple of comments. So one question is related to the globular cluster new detections. Okay. So these have been done with the same method of the Fermi collaboration, or likelihood ratio, or did you explore some other way to make the detection? Or
no, it was the standard method of the Fermi Lat collaboration at the time. But now in 4FGL they are using this weighted likelihood ratio. So I'm not using the weighted likelihood. I'm using the standard likelihood ratio.
I mean, one comment about it, you could explore the possibility that other globular cluster can be detected in gamma rays using machine learning algorithms like MST, DB-scan. Maybe you'll find more detections. Has been successful in blazar physics in the past. So, because when you find a detection, then when you find a detection with a different method, then it will be included in the list that people creating the catalog will use in the future. And so you can detect one source with another method, and then having detected with a classical likelihood ratio in 5FGL. Okay, so okay. One additional question is related to the following ones are probably all related to the low luminosity AGN. So can you show in slide number 25, there was the radio gamma ray correlation. So this one has been drawn using the Palomar sample. So I mean, okay. So all these ones are basically upper limits for the undetected ones. Yes. And then you have only the fourth one detected, correct?
Yes, correct.
Okay. It was not clear to me. So you are always tend to detect those that are brightened in radio, basically.
Yes, that's what we got.
Can you go also back a couple of slides again on this topic? When you were discussing the 197 selection.
Okay, it's here.
Yeah, correct. So, but okay, so you basically took all of them. Can you just get me a better idea about how they were? What are the selection criteria for the Palomar survey? So it's just the footprint in the sky, or did they make some cuts on the basis of the color when they did the selection?
No, there is a cut in magnitude. So these galaxies are really bright, and their magnitudes in the B band of the optical spectrum is less than 12.5. So these are really close, really bright galaxies.
Okay.
And they are taking only the spectrum of the central region of the galaxies.
Okay. So basically, okay, these three liners and the Seifert are probably all a redshift below 0.02, something like this.
Yes. There. The farthest source is this one, Perseus A.
Yeah.
And the redshift is 0.019, I think.
Yeah. But no, Perseus, the other three, I mean, NGC 315 probably I knew, but the other two were kind of okay.
Well, this one here is Messier 87, so it's quite close.
Okay. So just let me examine. Okay, fine. I just know the name of the other one. Okay, totally fine. Okay. The other question about the models, but basically Fabrizio asked because I was curious if you develop or not the model, but Rodrigo and Fabrizio already asked. My last point is only related to one thing I did not, even if I signed the paper and we wrote it together, I probably did not deeply thought about it. The connection, I mean, there is, even if the correlation is not very tight, but there is a sort of trend when you plot the spectral index in gamma rays versus the Q22 parameter.
Yes. Raffaele called my attention to that.
Yeah,
this one here, right?
Something that, just as a comment, we probably should think a little bit more about it.
Yes. Raffaele also told me something related to that because we discovered that, and we have to see.
Yeah, in the sense
if
that
there's something. Yes,
it's something to keep in mind because it's the two parameters are basically okay. The radio flux and the infrared flux are connected with the gamma ray flux. Okay, but so there should be some hidden variables here if you want to claim a correlation. Okay, but in principle, the spectral index in the gamma rays and the other parameters on the x-axis should be ideally estimated independently. Okay, so it's something just to keep in mind. It's something that can be working on. Okay, I think I asked all the questions and check all my curiosities. Okay, so thanks again.
Thank you very much, Francesco, for everything.
Thank you very much, Francesco, for the comments and the questions. And now let's moving ahead to as we are getting closer and closer, and now we cross the ocean, and now we are inside Brazil. So now, Anna, you may proceed with your comments, questions, and everything.
Thank you, Rodrigo, for the invitation to be in the committee. It was a real pleasure to read such a nicely written thesis. And I would have had to stop in São Paulo anyway if I were coming from Italy. So in this way, yeah. Okay, so it was very nice to learn about the gamma ray universe, which I don't really check very often. And I thought the thesis was very well written and neatly organized. I really like the structure of the introductory chapters 1, 2, and 3, and the nice presentation with Canva.
Thank you.
Also, congratulations for having a thesis in English. I encourage you to post it in the archive later. Okay. So I have a few comments and curiosity. And a curiosity is a figure 2.2 that you chose M5. Why did you choose M5 to illustrate? And which bands did you observe at LNA?
Okay. Yes, I just chose M5 because I observed this cluster by myself in Pico dos Dias. And this was the only picture of a globular cluster that I had the right,
Okay.
So, I choose this one.
So it's just for
what,
fun.
What page, Anna? What page? What figure are you talking
figure
about?
2.2.
2.2.
The M5 globular cluster.
Okay.
So a general comment that there are several, I think, LaTeX missing spaces before Greek letters or expressions. I think this is probably because you did pre-definitions and forgot the sim. Maybe you can check that before. These were the only typos. For instance, page 60, at the end of, let me see, at the end of page 60.
Page 60, okay.
There's a 2 and a gamma together.
Wait, page 60.
Or is this my print that did? Well, it's just spaces, but nothing. I can send you later.
Okay.
Nothing that prevents from reading, but it's just editing for the end. So I'm not going to ask too many questions, as most of the thesis is outside my area of expertise, and there are plenty of specialists in these parts. And I'll follow most of my questions on chapter 4, the gamma ray emission from GCs in the Milky Way. Okay. So one thing is that you use the latest version of the Harris catalog in your 2019 paper for the Fermi Large counterparts. But there have been several bulge candidate GCs, heavily dust obscured, found by the VISTA survey. And do you think that you might find more GCs in gamma rays if you check those?
I remember that you mentioned that these clusters, I think a few years ago.
Did I?
And I think so. And we can find them, probably. But the problem is that they are in the center of the Milky Way, right? They are in the bulge. So this region is really hard to work on gamma rays because we have a lot of foreground and background emission from Milky Way. And we don't have a perfect model for the galaxy in gamma rays. And lots of these clusters can be absorbed by the emission of the galaxy depending on the model. So we cannot trust very much the gamma ray emission model for the galaxy, especially in the galactic center. It's very hard to believe. You can still do a lot of science, but you have to be very cautious.
It's because I'd ask this question probably again, because when you look at the correlation with metallicity, that you should have more millisecond, the number of millisecond pulsars should be larger. It's very promising to look in the bulge globular clusters because they should be more metal rich. So
yes.
They might even have more signal. So if you manage to model the galaxy well with some novel technique, it might be something worth looking at.
I hadn't think about that, but now that you mention it, yes, it may be a very good idea. I will take a note here because it's something I want to check.
Great. Okay. Any plans to extend this kind of study to other extragalactic systems, like with the globular clusters, or the large uncertainties in the pointing and matching would prevent that?
Actually, the sensitivity of Fermi-Lat prevents that. If I want to try to detect the globular clusters in Andromeda, for instance, which is here, I cannot. I simply cannot because we don't have sensitivity, neither resolution to do so. But maybe we can use it to detect compact dwarf galaxies like Messier 32 and maybe Messier 110. Actually, I already checked these two galaxies and the signal is really low. That we cannot claim anything, but these are systems more likely to be detected than extragalactic globular clusters.
Okay. And the last question I have, well, the one before the last, I apologize if you hear a dog snoring. It's sometimes it's hard. He's making a lot of noise. Several GCs of the Milky Way and also young massive clusters in the LMC and SMC have multiple populations detected. Out of curiosity, have you checked if the GCs you found with gamma rays have these multiple populations?
No, actually, a friend of mine from IAG told me about these clusters with multiple populations, but I didn't. And I think it's really a to do, because maybe this difference can affect the gamma ray emission. I don't know exactly how on the dynamics of the cluster and then on the formation of millisecond pulsars.
Yeah, but
So,
because this
for my curiosity, is different population, multiple populations of stellar populations, you mean?
Yes.
Yes.
So,
okay. And what's again? This is my curiosity, but what's the reason? Because I thought that it was quite homogeneous, the population of a given globular cluster. So, what would be the reason for the multiple populations? Is there a suspicion?
There are several models, and since 2000, I think 5, there have been many papers, and none of them are able to explain no model is able to explain. If there's a review in 2018 or 19 by Bastian and Lardo that has all the list of the clusters, and there's the multiple populations you can see also in the spectra with different abundances, and in the photometry in the CMDs, there's splits in the CMDs, and maybe, I don't know, some people from a different area with gamma rays might give new insight to this field if there is worth checking. Well, we can talk about it later.
This is a very
maybe Raniere, the outliers in that correlation between what was it? There was, I forgot the plot, but there are some outliers. Maybe they have a weird stellar population.
I can send you the papers later and we can have a look.
Yes, please.
Okay. And the last question, the spectroscopic follow-up with SOAR you did on the last part of the thesis. How did you select the sample to be observed among all the possible ones in the WISE color
No.
diagram?
We select these BCUs from the Fermi Large catalog.
Okay.
So we have a list of BCUs there. And from this list, we select those with the highest optical magnitude as given in the IAG.USP, I forgot the name of the catalog. It's the Naval Research Lab catalog. So we took those blazars with the which are the brightest, and we observe them. And this is not a very precise way, because the magnitude of blazars is something that is really variable. But this is how we do.
Okay. Okay, that's it. Thank you.
Thank you very much, Anna.
Thank you, Anna. Thank you very much for your input. And now let's move on to Zulema. So Zulema, you may begin. And your mic is mute, Zulema.
Yeah, sorry, I forgot.
Now we can hear you. Yes.
Yes. Well, first of all, congratulations for your thesis. I think you did a very, very good job. I follow your job from the beginning because I was your relator, and then I had to. And really, it's amazing what you were able to do in 4 years, or I don't know if more, but that's it. And I think it's very well written. Your English is very good. And I think you have very, for you, it's very easy to write. So that's something that it's you know, for a researcher is something that it's very important. My questions are not many because you already published the paper, so I don't have too much to ask. But I have some questions that at the introductory chapters. For example, let's start with page 33. Try to understand what I wrote in here. Yes, you say in the after when you start talking about pulsars, you say that when the spin axis is inclined with respect to the magnetic dipole axis, an electromagnetic radiation is emitted in pulses out of its magnetospheric particle acceleration sites. Why is it that it's emitted in pulses?
Let me just check this part of the text.
Is the first paragraph in section
2.1.1.
Okay.
Yes, okay.
You say that the radiation is emitted in pulses.
Oh, well, yes, I think I should be more clear here, but the pulses is just because the pulsar is rotating. So
Okay. So you have to say that because if a student reads that, it will think that the radiation is emitted in pulses. You see that the radiation is continuous, okay?
Mm-hmm.
Okay. In 38, page 38, let's go with order. So, yes, you talk about the last paragraph or the paragraph before the last. You say that the emission takes place in vacuum regions. What are these vacuum regions? What do you mean by vacuum regions?
Let me take a look here. I'm in the paragraph. So slot gap, outer gap.
What?
Okay. These are regions depleted of magnetic field lines.
Oh, okay. So it's vacuum because there are no magnetic field lines.
Okay, I see.
Yes, I don't know because, you know, my knowledge about pulsars are before the fast pulsars, and nobody talk about that. And so it's okay. So there are no lines in there. Then the next page, in the next page, you have a figure that you took, I guess, from nature. Where you where the magnetic lines are shown, okay? The dipole and the light cylinder and so forth. And my question is, where do the magnetic lines go? They just stop there?
No. They continue, but they are open. They cannot close anymore because these magnetic field lines.
Yes, but in principle, that's where the particles are accelerated, probably.
Yes.
Really, yes. And I don't think they follow a dipole form. They will go through. They won't pass across the light cylinder, I guess. They
will pass across the light cylinder and continue in a current field.
Yes, it's better not to take this picture that probably is a picture for, people, not physicists, but to do a real physics.
Okay, it makes sense.
Because it's a very ugly picture, I think, for a physics.
Okay, I see.
Okay, let me see what else. Page 47. Uh, 47. Yes, what is in there? Oh yes, no. That you are talking about the likelihood ratio method, and I asked here if it's going to be described, but it was described later, so that's not a question really. It was just a comment for myself. In page 49, yes, in the outer gap acceleration, okay? You speak about the plane of curvature. What's the plane of curvature?
Okay. If you have a magnetic field line,
yes.
This line is curved, this line describes a plane. This is the plane we're talking about.
Okay. It's the plane of the line. 49, 51. Yes, in 51, you are you talk about the different processes of emission. You say synchrotron, Brera, and inverse Compton. Okay, and then when you use it as self-synchrotron. You don't use external Compton. Is there a reason for that?
Let me just check the paragraph. Are you in section 3.2?
Section 3.2.
Okay, the first paragraph.
The first paragraph, you just mentioned the different emission procedures. And you say synchrotron, Brera, and inverse Compton. And then after that, when you use it in the next chapters, you use it as self-synchrotron, and you don't put any external Compton. Is there any reason why don't you use external?
Okay, no. Well, actually, no. There's no specific reason.
No, because when you model your low luminosity AGNs, you use only inverse Compton, and maybe you should put also external Compton in there.
Yes. Generally, we use external Compton when we have a classic AGN from which the amount of photons from the disk is very high. So we have a lot of external Compton in this case. For a low AGN,
well, but not necessarily from the disk. You have only the broadline regions, and when we come back to the
if I can interrupt, I think that there is no broader region in these sources. Basically, the radiation.
There are no what? No what?
Broadline region.
I don't know. You know, in the central source of Perseus, it's a. I think there are broadline regions in there.
No, from 87, no. Basically, there are.
No, not from 87. From Perseus, the first one.
Okay.
Yes.
But I guess the radiation energy density is too low. to be important, probably.
I don't know, because some of the sources are quite strong. But that's a question. You say that you're going to maybe study in more detail the processes that lead to the ACID. So maybe when you do, just check if that's something that can, because it's not necessary to account for all of the emission. You can have self-synchrotron and also external Compton and also hadronic models all together. There are lots of models that fit very well, blazars and flat spectrum quasars using several ingredients for the model. It's not possible to say that you have to reject one model and include the other when you can have both. Okay, so that was my comment. Okay, that's 51. Well, and then yes, I have in page 89. Let me see, where is it?
Another thing about this point, also besides the point that Fabrizio mentioned, that the radiation density for even if there is some feeble broadline region in low luminosity AGNs, the radiation density should be quite low to account for this external Compton, but also maybe photons from the dusty torus. The dusty torus also disappear for low luminosity AGN. So
yes.
So, yeah. Yes. But maybe in a more detailed study of a few low luminosity agents that we know there is a feeble broadline region might be worth it to do for the external Compton.
Exactly. Yes, in page 89 you present the graphs with the detection and non-detection. That's one of the many graphs in which you put non-detections. And my question is the following: we have 4 points or 5, I don't know, that are detections, and a lot of non-detection. Does it make any sense to make a correlation using both? I know that you can put non-detections inside correlations, but I think that's worse when you have many detections and a few non-detections. What's the meaning of putting lots of non-detections when probably the non-detections are due to the instrument you are using and not a real thing?
Actually, these non-detections, these upper limits, can restrict our correlation. So if there were lots of upper limits below the correlation, so this should mean something. In our case, indeed, you are right. They do not make too much difference. They would make difference only if they were very low.
Yeah, exactly. But anyway, that's just a comment. And finally, regarding the last 3 works you did that in collaboration with lots of people, and you published papers, and the papers really reveal the work of the group. For example, you say, for the last 10 years we were observing, and it was not you who was observing the things. So I think that instead of copying the abstract of the papers you published, you should put more what was your contribution to the papers. For example, I don't know if you made the observation, how much of the reductions you did. Maybe you did everything, or maybe you didn't do anything. It's not clear for a thesis, okay? So it's not a criticism, but I think it would be nice if in the thesis it's clear what was your contribution to the paper.
Okay, in these 3 papers, I was indeed leading these papers. So I did much of this work. Of course, I had help from Francesco and from some of my friends, but I was behind everything in these papers. Yeah. And in the last paper, for instance, I did the optical spectroscopic observations and I did the data reduction. But half of the observations were done by one collaborator of mine, but only half of the observations. The reduction was made by me and the other half of observations by me. And I wrote the text and everything.
Yes, I imagine that you wrote the papers, you're the first author, and certainly, but it would be nice if it's clear in the thesis that you did all the work and used some of the data of your collaborators. I mean, it would improve the way we see your work, okay? So that was a question that I wanted to ask you because it's not clear when you have a paper with many authors, how much was your work and how much was the others. And since it's your thesis, you should make clear that you did the work, okay?
Okay.
So that's it. And again, congratulations. I think you did an excellent job. And
thank you very much, Zulema.
I can add a comment, no, regarding the papers Raniere was doing in Italy. I can tell you that some of the things written in the paper, I'm not able to do it. He just did by himself. Okay, so.
No, I'm not doubting it, you know. I just think that it would be better if it's clear in the paper that he did it. That's all.
Highlighted in a better way, I see. Okay.
Yeah, so maybe, Raniere, in the thesis, you can put a couple of sentences basically saying what you told us here. Look, yeah. I did basically everything. This is specifically what I did or something like that. It's very easy to implement.
Yes. Sure.
So thank you very much, Zulema, for your comments and the many questions that certainly enriched the discussion. And now let's go to the final committee member. So Gastão, please, you have the floor.
Thank you, Rodrigo, and thank you for inviting me for this thesis. I was even a little bit surprised because I'm quite an outsider of pulsars and gamma rays and most of the things that
we don't see, at least with the 9 years of data.
Okay. Well, it's I think it's surprising. And yeah, I have another.
There will be the formation of clusters. But for the smallest clusters with a few thousand of stars, we cannot guarantee that the amount of millisecond pulsars will be high. So for these clusters, there are not populations of millisecond pulsars, just because the number of stars is very small.
I see. Yes, I noticed that you had at least 10 or some tens of millisecond pulsars in a global cluster, I think.
Yes, the faintest gamma ray global.
In the sheet.
Yes, yes, I see.
Okay, that's okay. Yes, I have another question. In clusters of galaxies, usually you have a huge galaxy in the center. It's the brightest cluster galaxy, the BCGs. I think most of the time they are CD galaxies, so very huge galaxies, a huge envelope. And usually, it's very often, they are radio sources. And I was wondering, do you detect those galaxies in gamma rays? Do you know about that? Has it been done?
Well, is Messier H7 and Perseus A, are them BCGs?
Yes,
Perseus A?
they are. Yeah.
Okay,
they are
so
not the galaxies properly, but they are the brightest galaxy clusters.
okay, so these are two galaxies in our sample. But I think we detect them because these BCGs tend to be active. Am I right? They tend to be. So these
nearby.
They are nearby and they are active. So maybe it's not the fact that they are BCGs, but by the fact that they are AGNs that we are detecting.
The fact that they have radio emission, I think, because there's a correlation, I understood.
Yes, yes.
With the radio emission and the gamma ray emission. So I was wondering. And yes, it's a technical question. What's your lower limit in flux that you detect in ergs per second per centimeter square?
Okay, in ergs per second, I don't know, but in photons per second, for Fermi, it's typically 10 to minus 14 photons per centimeter square per second.
Yeah, well, that's
actually,
very hard for me.
It depends a little bit on where you are in the sky, because you can filter better the background or not, depending on your latitude.
Yeah, because I was looking at your table. Let me see if I find it again. It's the one of globular clusters, actually. And you have, yes, it's table 4.1. Table 4.1, you give the clusters, you give the luminosity and the energy flux. And so I was looking at the energy flux, and it's 10 to minus 12 erg per centimeter square per second.
Yes.
And I think it's quite a high flux compared with X-rays, for instance. I thought you could go even deeper, even to lower energy flux. So that was my question, my curiosity. What's the minimum energy flux you can detect with Fermi?
So as you can see in this table, the very last source, Messier 79, it has a flux of around 1 times 10 to minus 12 ergs.
Yes.
Per centimeter square per second. And this is in the limit of detection of Fermi-Lat. But detection, I mean a 5 sigma detection. We can go to a smaller flux, but the significance will be, 3, 4 sigma. So this value is quite close to the bottom of the telescope.
Okay, so 10 to minus 12, let's say. Okay. I ask that because in X-rays, we can go to 10 to minus 14, for instance, for very deep observations. And, wow.
The fact is that in the X-ray, you can focalize. Here, no.
Yes.
Focalize gamma rays. And so the background cannot be also the number of photos, of course.
Okay, yeah. And you cannot focalize gamma rays. And but even so, you have a huge equivalent effective area. You mentioned somewhere the effective area of Fermi-Lat, and it's not small; it's big actually.
Yes, it's starting at.
But do you consider 1 square meter large, Gastão, for X-ray standards?
For X-rays, yes. X-ray telescope has smaller, yeah.
Yeah, but the number of photons is
yeah, right. You can point there during hours and focus the photon. So that's different. I agree. So it's just a curiosity, okay? I'm just learning. Okay, let's go on. Yeah, I have another question about blazars. Do blazars have a duty cycle? Does it turn on and off, or it doesn't? Because we think that AGNs may turn on and off, and they have a duty cycle of say 10 to 8, some 10 to 8 years.
And actually, I never heard about a duty cycle in blazars. I don't know if there are people looking at it, but I never heard about.
Okay, it's a curiosity. It's because we talk about that on for AGNs, and even in Perseus, we believe that we see that because you have a system with 2 bubbles that we see in X-rays and 2 closer bubbles, and the difference is that the AGN was active at some point in the past. It turned off, and then it turned on again, and they are blowing these nearby bubbles. So there is a duty cycle implied in the observation. So I was wondering if blazars would show that, what is known about that, and if it appears on, well, in gamma rays, maybe not, but okay, another curiosity. And let me see. Okay, now actually, I think I'm okay with that. It was really a very nice reading, and I have two questions. One is, what will happen when Fermi stops functioning? What will be the next very big, very nice gamma ray satellite?
Okay, there is not a directly a direct successor for Fermi-Lat, but in the next 10 years or so, we will have CTA. CTA will be in the next few years, yes, which start observing gamma rays from 10 gig electron volts. And we will have in around 10 years, 15 years, maybe, I don't know, Amigo, which we will observe gamma rays up to 10 gig electron volts. Okay. So the Fermi-Lat band will be covered by these two observatories in the future, but if it crashes now, we don't have a
backup plan.
There are no plans for a telescope in the next few years in the Fermi-Lat band.
Oh, okay. And the last question is, what are your future plans? Are you going to a postdoc somewhere, staying still at Lima?
Yes. Actually, I got a position in Trieste, a postdoc position in Trieste.
Oh, nice.
And
congratulations.
I was supposed to be there by the end of this month, but I'm having problems with the documentation because of COVID-19 restrictions, and now I don't know exactly what I'm gonna do. I want to do a postdoc, of course I want, but maybe I'll have to be patient and wait a little bit more.
Oh, okay. Oh, so you're not sure you can go to Trieste. If you don't go at the end of the month, you lose the position.
No, I can start next year. So the position is I have the position there. It's hold for me at the moment, but I was approved, I think, in May. And by now I still don't have the documentation because of these problems.
Okay. Well, yeah, it's very complicated times we are living. Anyway, thank you very much. And
thank you, Gastão.
I'm finished.
Thank you very much.
Thank you.
Okay, thank you. Thank you, Gastão, for your input. Thank you very much. Okay, so we reached the end of if there are no further comments or questions by the committee members, we reached the end of the questions session. And so, as usual, let me do first the Portuguese version and then the English version of what comes next. Todos os membros da banca tiveram a oportunidade de perguntarem sobre o trabalho ao candidato. A banca agora vai se reunir numa sala virtual, privada, para discutir o trabalho, a tese, o trabalho de doutorado do candidato. E nós retornaremos a esta sala pública em cerca de 10 a 15 minutos para anunciar o resultado da defesa de doutorado do candidato. E agora em inglês. All members of the thesis committee, they had the opportunity to ask questions, interact with the candidate. So now the thesis committee will convene at a private online room for discussing the PhD thesis work. And we will meet back in this room, in this public room, in about 10 to 15 minutes to announce the result of the candidate's defense. So now I would like to ask everybody so you have already the link to the private room. So all the members, please join me in the private room. And we will back here. Do you all have the link?
Yes.
Okay, cool. Okay, so see you there.
Okay.
Tchau, tchau, Raniere. Até daqui a pouco.
Até logo.
Oh, sala errada.
Olá.
Olá.
Ok.
Ok.
Estamos de volta. So, vocês podem continuar.
Eu estou ouvindo bem.
Ah, tá ótimo. Então, só para testar o áudio. Ok, então, os membros da banca, nós nos reunimos, nós discutimos o trabalho, a qualidade do trabalho. Todos os membros da banca foi unânime que estamos impressionados com a quantidade de trabalho e a qualidade do trabalho realizado no doutorado. E assim, nós gostaria de anunciar, decisão unânime da banca, que o candidato foi aprovado para o título de doutorado por unanimidade. Então, parabéns, Kelly. Parabéns.
Muito obrigado, muito obrigado.
E foi fantástico. Então, temos um novo doutor. Vou anunciar em inglês também. I'm happy to announce that the candidate has been approved with unanimity for the PhD degree. So, congratulations for the title.
Thank you very much.
Yeah. You are now doctor.
Parabéns.
Obrigado, muito obrigado. Thank you very much.
Okay.
Grazie mille.
O champanhe para o ano que vem, né?
And again, and again,
italiano.
Como é, Gastão?
Marolo, sei lá.
Sim. And again, obrigado aos membros da banca novamente por estarem aqui. Thank you for all the committee members. Thank you very much for taking your time, for being here. Yeah.
A pleasure.
It was a pleasure.
Thank you. Yeah.
Thank you very much.
Okay. Bye-bye.
Okay.
Bye-bye.
Bye. I'm also going. Thanks, everybody. Thank you very much. Thanks again, Raniere. I really enjoyed working with you.
Francesco.
Thanks, Rodrigo, for sending Raniere and for the collaboration.
E parabéns, Rodrigo, né?
Parabéns.
Stay healthy, everybody. Stay healthy.
Yes.
And
thank you, Francesco.
Okay.
Yes.
Thanks a lot. Thanks. Bye. Ciao, Fabrizio.
Ciao.
Ciao.
Ciao, Raniere.
Tchau, parabéns.
E Raniere, vamos para uma sala para fazer a gente conversar e celebrar.
Bora lá.
Vamos lá. Raniere, você quer você criar a sala e compartilhar comigo, daí você pode compartilhar com quem mais você quiser, colocar no Slack. Pode ser? São Paulo, e assim nós encerramos o evento do doutoramento do Raniere. Muito obrigado a todos que estão nos assistindo ainda.
Tchau.
Tchau.